essentially the question that we are asking ourselves as far as relative stability is concerned. Okay, so now that we understand what is relative stability, right, what do we mean by that, right? So the question that we need to ask ourselves, see, this is a very qualitative discussion, is it not? See, you plot the open loop poles, that is the poles of the transfer function, of the system transfer function, and say, hey, look, this system is relatively less stable than the other one, right? But then we need to have quantitative measures which essentially help us in taking a decision, right, when we do control design, right? So then the questions that we need to ask ourselves are the following. So the one question we can ask is the following, what are measures of the degree of stability? Of a closed loop system. Okay, that's a question that we need to ask ourselves, right? To answer this, let's revisit our standard feedback system, okay, that we have been considering, where the forward path transfer function is G of S. Okay, the feedback path transfer function is H of S. Okay, and there is an error E of S, right? So then please note that Y of S divided by R of S is going to be equal to G of S divided by 1 plus G of S H of S. Okay, so that's what we are going to have, right? Okay. Now what's going to have we are going to look at is essentially we are going to look at the closed loop characteristic equation, okay, because the roots of this equation are the closed loop poles. Suppose, let's say, the closed loop system is stable to begin with, right? Then we know that all closed loop poles are in the left of complex plane, okay. Now due to some parametric uncertainties, the closed loop system is on the verge of instability. But then you see that if my closed loop poles are in the left of plane to begin with, they can essentially transition to the right of plane only when they go through the, what is the boundary between the left of plane and the right of plane? J omega axis, right? So that is essentially, that's why it's called as the stability boundary, right? So essentially the J omega axis or the imaginary axis is the boundary between the left of plane and the right of plane. So if my closed loop system is stable to begin with, the closed loop system poles, if they are migrating closer and closer to the right of plane, they have to necessarily pass through the J omega axis, right, which is the stability boundary before they go to the right half plane. Do you agree? So we can use that to our advantage, okay. So the point is the system or the closed loop system would become unstable when its poles cross the J omega axis, right. So of course the presumption is that to begin with the closed loop system is stable, right. That's when all this discussion makes sense, right. So that is on the J omega axis, what will happen? The closed loop characteristic equation will become this, right, because S is of the form J omega. Do you agree? Right. So this is what will happen to the closed loop characteristic equation. So in this scenario, then J omega, Gj omega, Hj omega will be equal to -1. Okay, so that is when, what is the scenario? That is the closed loop poles are in the left of plane and they are migrating to the right of plane due to whatever reason, right, some parametric uncertainties, disturbances and so on. So then they need to cross the j omega axis. Let us say you stop when they are crossing the j omega axis, some closed loop pole, right. So the closed loop characteristic equation is going to satisfy is going to essentially become 1 plus g j omega h j omega equals 0. I can rewrite it as g j omega h j omega is equal to minus 1. So what is g of j omega h of j omega? That is what we have been reading in the frequency response, right. It is the open loop sinusoidal transfer function, right. So that is the function g of j omega h of j omega. So let me write it one more time. So g of j omega h of j omega is the open loop sinusoidal transfer function. Okay, so that is what it is. Okay. Now, what are we interested in then? So, the question is, the system would become unstable when the Nyquist plot of g of s h of s, right, passes through the minus 1 point, because if there is some value of s which makes the value of g of s h of s to be minus 1, right, then the system would become unstable, right. So, or in other words, I can reinterpret this as the following: the closeness of the g of j omega h of j omega to the minus 1 point is indicative, of course minus 1 point in the g of s h of s plane, is indicative of relative stability. Okay, so that is what one could conclude, right, from this. So, see what does it mean? Let us say I have the g of s h of s plane, right. So, let us say this is my minus 1 point, right. So, okay. So, let us say like I have, let us say some what to say Nyquist plot, right. So, let us say some systems Nyquist plot which essentially let us say starts from the origin and then goes like this, and or let's do it this way, right. So, let us say comes like this and goes like this. Okay. So, another system which essentially comes and goes like this. Okay. So, you see that the second system is going to be closer to the minus 1 point. You perturb it, you stretch the Nyquist plot a little bit, it can pass through the minus 1 point maybe, right. So, the closer the locus is to the minus 1 point, the less relatively stable that system is, right. So, that is what we can conclude about conclude from this particular discussion, okay, on relative stability. Now, note that the minus 1 point in the g of s h of s plane means the magnitude is 1, the phase is minus 180. I am writing minus 180 because like you see that typically we deal with proper transfer functions, you will understand it shortly. So, of course minus 1 point in g of s h of s plane indicates that the magnitude of the open loop transfer function is 1 at that point and the phase of the open loop transfer function is minus 180 degree. Do you agree? So, I am just writing in terms of magnitude and phase. We are going to use this idea to define a few parameters that can quantify relative stability. Okay. So, that is what we are going to do now. Okay. So, are there any questions? No. Yes.
So that closeness, you get this knowing this first or you do that first?
Sorry, which one?
The closeness of the G of J.
So that follows from this, because you see that, see what is the scenario we are considering? Let us say we go back to this, right. You plot the Nyquist plot of system 1 and system 2, it may look like what I have plotted, right. So because the closer it is to the minus 1 point, you know, like if you perturb it, it can pass through minus 1. What does passing through minus 1 mean as far as the Nyquist plot of the open loop transfer function is? That means that S equals j omega satisfies the closed loop characteristic equation. That means that a closed loop pole is going to be of the form j omega. In other words, you are going to have closed loop poles on the imaginary axis, and that's what we are discussing, right? So that is why we are breaking down the problem, or not breaking down, or converting the problem of analyzing closed loop stability once again into a problem of analyzing the open loop transfer function. See, that's a big advantage with frequency response methods. So one advantage with frequency response methods, if you go back and think through, is that even in Nyquist stability criteria, you know, like we are looking only at the open loop transfer function. Even here, I am looking only at the open loop transfer function, not at the closed loop transfer function, right? So you don't even need to calculate the closed loop transfer function. You give me the open loop transfer function, I can analyze its Nyquist plot and then tell you some information of the closed loop system. Okay, so that is the impact here. Okay, so you see that I can rewrite this closed loop characteristic equation in this form. All right, so as g of j omega, h of j omega equals minus 1. If there were a closed loop pole on the j omega axis, that's the scenario we are considering. Okay, yeah. Okay. So minus 1 point in the g of s h of s plane means the magnitude of g of s h of s is 1, and the phase of g of s h of s is minus 180 degrees. Okay, is it clear? Okay, those are two important ideas. Okay, so based on this, you know, like we are going to essentially have a few definitions. Okay, so let me essentially write down those definitions. Okay, the first definition is the following. Okay, so we are going to define what is called as a gain crossover frequency. Okay, I will define these two frequencies, then we will come back in the next class and then define two important parameters. Okay, I just want to spend some time discussing those, right? So what is this gain crossover frequency? Okay, it is the frequency, it's denoted by omega g. Okay, the gain crossover frequency omega g. It is the frequency at which the open loop sinusoidal transfer function magnitude becomes equal to 1. Okay, so the magnitude of the open loop transfer function should become unity or 0 decibels. Okay, if you convert to 0 decibel measure, obviously if you take logarithm of 1, you will get 0, right? So that is the definition of the gain crossover frequency. It is the frequency at which the magnitude of the open loop transfer function becomes 1. All right. Then we have another definition. All these are definitions, please remember that. Okay, we have another definition which is what is called as a phase crossover frequency omega p. What is the definition of phase crossover frequency? It is the frequency at which the phase of the open loop transfer function becomes minus 180 degrees. Okay, so that is the definition. So of course you can immediately see how these definitions are motivated, right? Because why? The minus 1 point has a magnitude of 1 and a phase of minus 180 degrees, right? That's motivating these two definitions. Okay, so of course if omega g equals omega p for some particular open loop transfer function, what does it immediately imply? That the open loop transfer function is passing through the minus 1 point at that frequency. Is it not? Think about it, right? If omega g equals omega p for some open loop transfer function, then at that frequency the magnitude of the open loop transfer function is 1, phase is minus 180. What point does it correspond to? The minus 1 point in the g of s h of s plane, right? So let's quickly do this example. Okay, the example that we considered today. So let's say we consider g of s h of s to be 1 divided by s times s plus 1, g of j omega h of j omega to be equal to 1 divided by j omega times j omega plus 1, right. So, what is the gain crossover frequency? Can you calculate it, please? So, how do you get the gain crossover frequency? Gain crossover frequency, you equate the magnitude to 1, right. So, how do I get gain crossover frequency? What is the magnitude of this factor? It is going to be 1 over omega g times square root of omega g squared plus 1 equals 1. Am I correct? Then how can I calculate omega g from here? Of course, I cross multiply. This will imply that omega g times omega g squared plus 1 is equal to 1. Then what can I do? I can square it. If I square it, I will get omega g power 4 plus omega g squared. Right hand side will be 1. Okay. So, this will imply that omega g power 4 plus omega g squared minus 1 is equal to 0, right. So, if you solve this, this is a fourth order polynomial in omega g, but then you see that it is quadratic in omega g squared, right. It has only omega g power 4, omega g squared and constant term. So, if you say omega g squared is some omega g hat, you will see that you will get a quadratic equation. You use that notion to essentially solve for this. If you solve this, please do it, okay, and check this answer. You will get omega g to be 0.7862 radians per second, okay. Please check this answer, okay. So, that is what you will have. So, that is the gain crossover frequency for this particular open loop transfer function. So, this is the only frequency at which the magnitude becomes 1 for this particular open loop transfer function. Now, how do I calculate the phase crossover frequency? What is the phase of g of j omega, h of j omega? It is going to be 0 minus 90 plus tan inverse omega. Do you agree? I think by now, I think all of us should be familiar with these concepts, right. So, the numerator phase is 0, denominator due to 1 by s you will have minus 90 and then minus tan inverse of omega, right. So, this is going to give me minus 90 degrees minus tan inverse omega. So, when will this phase become minus 180 degrees? Right. So, the question becomes, when will this phase become minus 180 degrees? That means tan inverse of omega p should be 90 degrees, right. When will that happen? Only when omega tends to infinity. So, my phase crossover frequency is infinity. In other words, this essentially means that the particular open loop transfer function phase becomes minus 180 degrees only when omega tends asymptotically to infinity, which you can easily visualize even from the Bode plot. See, think about how the phase plot of this particular factor will look like. The phase will go only to minus 180 only when omega tends to infinity, right. So, that is why the phase crossover frequency is infinity, okay. So, we will stop here. So, we will build on these two frequencies in the next class, and then I will define parameters which can be used to quantify relative stability, and we would use that, okay. We will discuss that in the next class, okay. Fine, thank you.